You know when you grab a brand new 9-volt battery? Do you ever stop and think, am I really getting 9 volts out of this thing? Well, the surprising answer is kinda, but not always. That number on the label, that's the ideal world. The reality, though, is way more interesting. And today, we're going to pull back the curtain on the hidden world inside every single battery you use. All right, let's kick things off with a classic mystery, one you've probably seen 100 times. You get in your car, you turn the key, the engine cranks over, and for just a split second, the headlights get dim. What's the deal with that? It's not a glitch, I promise. It's actually a fundamental rule of electronics playing out right in front of you, and the answer is hiding inside your car's battery. So to really get a handle on what's happening in the real world, we first have to imagine a perfect one. Let's think about what a perfect power source would even look like. This is going to give us our baseline, our gold standard, so we can see exactly where reality, well, doesn't quite measure up. Okay, say hello to our theoretical hero, the ideal voltage source. Just imagine a battery that says 9 volts on the side, and it delivers exactly 9 volts, all the time. It doesn't matter what you hook it up to, a tiny little LED, a massive power-hungry motor, whatever. That voltage would just stay perfectly rock solid, constant. So what makes this thing so magical? Well, for starters, it would have absolutely zero internal friction, what engineers call internal resistance. None. It could pump out an unlimited amount of current whenever you ask for it, and it would be perfectly 100% efficient. No energy wasted as heat. It is, for sure, the superhero of power sources. But yeah, it only exists on paper. Okay, so that's the dream. That's the ideal world. But now, it's time for a reality check, because back here in the real world, there's a secret ingredient, a hidden flaw that changes the entire game. And yep, here it is. This is the simple truth that pretty much governs all of engineering, all of physics. In the real world, with real atoms and real chemistry, perfection just isn't on the menu. And that little fact brings us right to the heart of our mystery. So meet the, well, let's call it the antagonist of our story. Internal resistance. Here's a good way to think about it. Imagine your battery is like a huge, powerful water pump. The internal resistance is like a tiny, narrow section of pipe right at the exit of that pump. It doesn't matter how powerful the pump is, that little bottleneck is always going to slow things down, especially when you try to blast a whole bunch of water through it once. Every single real battery has one. So now that we've met our hero, the perfect ideal source, and its real-world counterpart with its secret little flaw, let's put them side by side. This is where you're going to see exactly how that one tiny thing, that internal resistance, makes all the difference in the world. Check this out. On the left, you've got that perfect theoretical world. Steady, constant voltage no matter what. But on the right, that's our world. Because of that little internal resistance, the voltage you actually get from a real source drops the harder it has to work. And by work harder, I mean the more current it has to push out. That drop is everything. Right, that voltage drop, that's the whole ballgame. It's not a possibility, it's an inevitability. It's the direct result of having internal resistance, and it's the exact phenomenon that's going to solve our dimming headlights mystery once and for all. Okay, so let's walk through it step by step. First, you connect something to your battery. In engineering speak, we call that a load. As soon as you do, current starts flowing. But here's the thing, that current has to fight its way through the battery's own internal resistance just to get out the door. And in that little struggle, a little bit of the voltage gets used up or dropped right there inside the battery before it ever makes it to your device. And you know what? It all boils down to this super simple idea. The voltage your device actually gets to use is the battery's perfect starting voltage, minus the little bit that gets lost on the way out. And how much gets lost? Well, that depends on just two things: how much current you're trying to pull and how big that internal resistance is. The more current you demand, the bigger that internal voltage drop becomes. Now, you might be thinking this resistance must be huge to cause any problems, but it's really not. For a brand new AA or 9-volt battery, this internal resistance is actually tiny. We're talking often less than a single ohm. It's small, for sure, but as you're about to see, its effect can be pretty dramatic. So let's see this in action, because this makes it really clear. With nothing connected to it, no load, our battery measures a perfect 9 volts. Awesome. But now, let's ask it to power a small LED. That's a pretty light load. See that? The voltage you can actually measure dips just a little. But now ask it to power a motor. That's a heavy load, demanding a lot of current. And whoa, look at that drop. The battery itself is the same, but the voltage it can deliver has changed, all because of what we asked it to do. Okay, so what? A tiny resistance, a little voltage drop? Why should you care? Well, because this isn't just some abstract concept from a textbook. This affects the performance, the design, and even the lifespan of basically every single electronic device you own. And this brings us right back to where we started. Your car's starter motor? That thing is a massive electrical load. When you turn that key, it pulls a huge surge of current from the battery. That huge current, flowing through the battery's internal resistance, causes a major voltage drop across the entire car's electrical system. For that one moment, your headlights are getting less voltage, so they dim. And here's the kicker. As a battery gets older, its internal resistance goes up. That's why an old battery has such a hard time starting a car, especially on a cold morning. This is so cool. It means that when your TV remote finally gives up, the batteries inside aren't necessarily empty. A lot of the time, their internal resistance has just crept up so high that they can't deliver the voltage needed under load anymore. The energy might still be there, it just doesn't have an effective way to get out. So I'm going to leave you with a final thought, something to chew on. The next time your phone suddenly dies on you, even though the little icon says it still has 10% charge left, ask yourself, is it really out of juice? Or did you just witness the very real and very powerful effect of internal resistance in action?
Thanks for watching.